By default, I think most of us go to dummy coding for handling categorical predictors. But contrast coding is also available. And the reason that it's important to know this is in particular for two kinds of situations. First, when the number of categories is quite large, maybe there are 10 categories to this variable, this predictor, and dummy coding those would mean 9 DF. 9 codes, and 9 codes just gets cumbersome. It totally can be done, and if you have to do it, don't worry about it. But you may not want to add that many numerator DF to your analysis. You may want to be more efficient about it. Second, dummy coding only allows for comparisons between the reference group and every other group, like individually. What it doesn't allow us to do is to compare two groups of groups together, if that makes sense. For example, if we had that 10 categories, is there any way to compare groups 1 to 5 against groups 6 to 10? Or groups 1 and 2 against the others? And the answer for dummy coding is no. But with contrast coding, we have that flexibility. It's much more power to detect effects because as we keep adding that K, our chances of seeing a significant result, if it's really there in the population, it dwindles. And so basically when we have an a priori theory of which group or groups differ from one another, then we can compare one set of groups against another set of groups and only do, for example, if we had 10, again, that is a nice example because it's just so many levels, then we can do maybe 2 contrast codes, one where we contrast groups 1 to 5 against 6 through 10, and then we contrast groups 1 and 2 against groups 3 through 10. And then we have only 2 DF we're using. We're going to put all our chips on the differences being seen there. And we don't have to test all possible things. We don't have to do post hoc in that case unless we don't find the results we're looking for. And then we're like, okay, let's do exploratory, which always happens, by the way. Even if you find what you're looking for, you might want to do post hoc just to see any trends and report to the reader, of course, transparently that we had these hypotheses, so we tested these contrasts, and then we did exploratory for the other differences to see if there were any hiding in the other groups and the other combinations. Anyway, so you're familiar with the post hoc test. We're not going to do that in this class, but I will show you how to do contrast coding. And again, the reason it's important, the reason that we can't do it in ANOVA is if we have other continuous predictors in our model. And so, this again could be a control situation where we believe that these 4 departments differ from one another in some way, and we know that up front. So we're going to put one contrast code up in the block 1 with the controls, and then our focal variables in block 2. In order to save DF and to increase power. In fact, I don't know if you've noticed this in your lab, but in my lab, I've noticed that our planned contrast will be significant, but our post hocs won't be, and that's just because contrast codes have a lot more power because you're dividing that p-value among all the post hocs as tests, as we know. So that happens fairly frequently. So I would say when you have any inkling of which groups should differ from each other, definitely use contrast coding. And I've seen this in industry data a lot, at least when I talk to students who've gone out into industry and they say that they'll have 20 categories, 20 departments, 20 or branches of an organization, let's say, in different geographic locations, and they're trying to let's say the client asks them, hey, can you see if any of these are different from each other? And that's a huge post hoc and only ANOVA. That just sounds really awful to do, to think about all those comparisons that you could make across 20 different branches. Can you imagine? So I think part of our job as data people in organizations and when we work with clients, we have to try to narrow down why do they want to know the differences across these locations. Do they have any indicators of which branches will differ from which other branches? And to let you know that so that you can test those contrasts at least have some that you're testing at the beginning before you're sifting through all the differences for 20 branches. And by the way, we're getting now, like when we're talking 20 branches or 30 branches, we're getting into MLM territory, but that is not this class. So MLM has some restrictions on it. It's great because assumptions, basically there aren't the assumptions that constrain us in MLM like they do here. But it's a long story and I can't go into the rabbit trail now because I don't want you to like focus on that. But just know that as the number of branches increases or categories increases and the people within them are increasing as well, maybe. So we have 30 branches with 10 people each in them or 50 people each. We're in a multi-level analysis situation that ANOVA, the way we know it here, like this older version of testing for mean differences that we have that's called ANOVA and regression too, is just not adequate to handle data like that. And so you're going to be in a different category, which you will learn later in the stat sequence. But for now, I think most of us, even those who work in industry, won't have access to that much data. And if you do, it's coming. All right. So we're doing the simpler. But honestly, I have heard of cases where people are dealing with 10 branches, 20 branches, and the client only cares about understanding, like, are there differences across in sales, maybe in retail across these branches? And it's like, well, you got to sit down with them and really think about why this is important, how to start with any kind of theory up front, because all those differences across all those groups, the possible combinations of differences are just too much for our minds to handle. So try to narrow them down to 2 or 3. Do you think these branches in this area will do better than these, and why? And then you can start to maybe, come up with 2 or 3 things to test, at least to start the ball rolling. Contrast and dummy coding always produce identical overall f-tests and r-squared, and their p-values will all be the same when we have the max possible orthogonal contrast in there. So remember, the number of orthogonal contrasts we can have is the number of groups minus 1. It's kind of like the same as dummy coding. And so dummy coding and using all possible orthogonal contrasts will produce the exact same overall results, and I will demonstrate how that works here in a bit. Okay, so that's a basic introduction. Now, creating the contrast code. Let's move along to this. So, hypothesis for code 1, contrast code 1. We're going to use our same example just to keep it simple with our departments, our sales, etc. And we have a theory that sales will differ from the other 2. So if that's the case, then we are going to assign it a -2 and then the others a +1. So you probably did this in ANOVA as well, I'm assuming. And then we have a contrast code 2. So remember, we can only do 2 and have them still be orthogonal. So we're going to leave sales out of this one, and we will just focus on the difference between IT and accounting. So 0 kind of takes sales out of the mix completely, and then IT and accounting, we're going to contrast those 2. Now, I just want to give you a quick word, and I think Field talks about this too in the textbook, but we can also easily imagine that these 2 groups represent 2 treatments, 2 kinds of therapy, maybe 2 kinds of training in an organization. We assume that one will be better than the other, but both will be better. I mean, either one of these will be better than the control. So imagine sales as the control. And so that's a perfect setup for this kind of scenario, because we're assuming that first we're going to test the control against the other 2, an average of the other 2, and then second, among the 2 kinds of intervention, which one is better? And so if this contrast code comes out significant, then we know that one training is more effective than the other, and that's good to know. If this one comes out significant, we know either one of them are better than nothing. But if this code comes out non-significant, that means that we can take the cheaper option of whatever these two are, meaning that they're both better than the control, but they're not different in relation to each other, right? So in the background, as a data person, like, it's so much more than the math. You're making decisions about people, about what's working, what's not working. Maybe you'll be hired by the government one day to, I truly hope our government will invest in science at some point. But, there are many programs in government where people need to evaluate their effectiveness and be able to close down the ones that aren't working or revamp them. And so this is a situation where, contrast code 2, you have two kinds of interventions, two kinds of programs, and imagine that they're not significantly different from each other. Then you would conclude, well, we can either do away with one or we can revamp them both to make them better, or the one to make it better, and then see. So, there's all kinds of possibilities when we're thinking about, doing program evaluation, doing field experiments maybe, where we have, we're contrasting two different treatments of some kind against a control, and then the two treatments against one another. So these two codes are orthogonal, and I'll show you why coming up. So let's move to that now. The contrast must be orthogonal, as you know from the prior class, and that means that two things have to happen. First, both contrasts weights, we call these weights, sum to 0. It's like we create a code with weights. It's weird, right? So the weights have to sum to 0 for each code, and then we have to multiply the weights together across the codes, and we add those up, and it's also 0. So if we multiply these two, it's 0. So the product row here is the information we're interested in for this. 1 times 1 is 1, and then 1 times -1 is -1, and so 0 plus 1 plus -1 is 0. So I will never ask you on an exam to create 2 or 3 contrasts that are orthogonal to each other from memory. On exams, you have limited time and focus, and this is something that you can always look up in a reference book and have time to figure it out. But you do have to know that they have to be orthogonal. You have to know what makes them orthogonal. But coming up with especially 3 or more contrasts, that can get tough, matching all the hypotheses to which contrasts, and that's work that takes a while and in practice, and so you'd want some time to do that. Please note that these weights can also, as long as this rule is not violated, that the weights sum to 0 for each contrast, and then the product, when we add up the products, they all sum to 0. As long as those rules aren't violated, we can use any numbers we want to represent these weights. And so I have in the notes below this slide, we could have a -1 here, and then a +1/2, +1/2. We could have a 0 here, and then a +1/2, -1/2. That is 0.5. So these weights, as long as these rules aren't violated, these weights can be anything. And so on an exam, I will not ask you to make any contrasts orthogonal to each other. I may ask you to create a contrast. So practice making a contrast that's the weight sum to 0 for different kinds of situations. Like if you have a two-group contrast, how could you make those weights? And that would just be a -1, -1, +1, +1. That's how I would do it. Let's see, for 3 groups where you're contrasting, but that's what we're doing here. 3 groups contrasting one against the other 2. That's just easy. -2, 1, 1. Imagine you had 4 groups and you wanted to compare group 1 to group 2, 3, and 4. So the mean of group 1 with the mean of the means of groups 2, 3, and 4. Then you could do, like, for example, a -3 and then a 1, 1, 1. So those are the things that I might ask on an exam that are relatively easy, and you could just create a contrast for that. All right, so this concludes the conceptual side of contrast coding. Just a quick review, understand why we need it, when we would pull out the contrast coding method versus the dummy coding method, and understand how many contrast we can make that are orthogonal, how many max can we have, and be able to create one contrast from memory for different situations that you might run into. And in the next segment, I'll show you how to create the contrast codes and then how to interpret the resulting output.